All right. Hello, class. This is AP Chemistry, Definitions of Acids and Bases. This is Mr. Harville, as I hope you guys would know by now. So we're going to dive into this. It's part of our acid-base equilibrium unit. It's kind of the beginning of it, and it's kind of starting to think about what really acids bases are in equilibrium solutions. Just a couple things you're going to need. Of course, your scientific notebook. That way you can take notes during this lecture, reflect back on them, make comments, questions, anything you want to ask in class. To do that, you're going to need a pencil or a pen. Specifically, you're going to want to probably do a pen, the way we've been trying to format it throughout this year. That way when you write it in pen, nobody gets to take your ideas or anything like that as well. You might need a calculator. Because we might have to do some Lewis dot structures later on. That way, if you're having trouble with adding or subtracting or anything like that, in regards to those valence electrons, you might want to keep that handy just in case you need that. And then, of course, your textbook. I would definitely recommend reading through this textbook as I'm doing this lecture, or at least following along, or use it as a resource if you've already read into it. So just have that handy just in case as well. So a couple learning targets we're going to do with this lecture. I can recognize different acid-base reactions based on the three definitions of acids and bases. This means that I can interpret the reactions and products of particular acid-base reactions that are based off the definitions used. I can develop a reaction mechanism for different acid-base reactions depending on the acid-base definition used. That's really wordy. But it does make a little bit more sense. It'll make a lot more sense probably by the end of this lecture, so just kind of bear with me here. This means I can interpret the chemical processes that are being demonstrated in an acid-base reaction for any definition of acids and bases used. I can utilize multiple definitions of acids and bases for the same reaction. Now, this is a learning target that is kind of the end goal here. I want you guys to, these definitions that we learn, I want you guys to try to apply these definitions in multiple ways to see how reactions kind of seem different in different perspectives. So that's kind of the end goal here, because I want you guys to start thinking a little bit more like scientists instead of just students. This means I can intuitively approach similar acid-base reactions with different perspectives to help interpret chemical phenomena, just like I just said. So how many definitions of acids and bases are there? Specifically, there's three main definitions of acids and bases that scientists use, and that means biologists, physicists, chemists, geologists, everything like that. First definition, probably the most common, something you probably have already dove into your general chemistry class, and we probably dove in a little bit earlier this semester, is your Arrhenius definition. We'll dive more into the specifics of that later. And then we have your Bronston-Lowry definition, which is a little bit more used by chemists and maybe biologists, and a little less of physics and geology. And then the Lewis definition, which is probably the most common, not most common, but most used to all scientists because of how useful of a nature it is and how general it is. I particularly like the Lewis definition because it's very useful for different aspects of chemistry. So we'll dive more into that. So Arrhenius acids and bases. So a little background. In the 1830s, it was understood that all acids had hydrogen, but not all hydrogen-containing molecules and compounds were acids. So in the 1830s, the scientists didn't actually have all the instruments that we have nowadays, which means that what they used to do is they used to take a solution, pour some acid into it, and I know this gas would form, and they were able to figure out through a variety of experiments that that gas was hydrogen gas. So they made the assumption that, oh man, so if I pour an acid in that I know is an acid, it produces hydrogen gas. So that's a general thing that they came up with. By the 1880s, Savante Arrhenius defined acids as a substance that release hydrogen ions into water. But what about bases? How can you define this in an aqueous solution? So let's kind of dive into that a little bit. And let's think about this a little bit more thermodynamically, and let's take a look at the ionic composition of water. So now we have water, it's in equilibrium, it's in a beaker, it's just tap water. Or actually, I take that back, let's not use tap water, let's use pure water. So we have pure water in a beaker, and in equilibrium it breaks up into these ions. So it breaks up into hydroxide and hydrogen ions. Now, one thing you need to pay attention to is the charges. So as you can see on the water, there's no charge to this. So as you probably remember from your general chemistry class, if there's no charge to it, it's considered neutral. So let's take a look at the hydrogen ion. Now it has a positive charge. Now we know, according to Arrhenius, that acids create hydrogen ions. So in regards to this, hydrogen ion would be considered an acid. Now, the most common thing about acids and base reactions is that to get a neutral compound, you typically have to add an acid and a base together. So if water is neutral, and we know hydrogen ion is an acid, that means it leaves hydroxide to be the base. And this is where the Arrhenius definition kind of comes into play. So this Arrhenius reaction incorporates that hydroxide ions, or substances that emit hydroxide ions, are bases. So keep that in mind, make a note of that. So just one thing, your state on equilibrium, again, we have this pure water in a beaker, and we have this equal amounts of hydroxide ions and hydrogen ions in equilibrium. So when it's in equilibrium in water, we should have the same amount. So if they add something to water and it introduces more hydroxide ions or more hydrogen ions, that water or that other substance is going to have to try to compensate for that by introducing the exact opposite to keep it in equilibrium. So let's take a look at some examples of this Arrhenius definitions of acids and bases. So first off, we have this sodium hydroxide, which is NaOH, and it's in water. So let's assume pure water, not tap water, it has all those electrolytes and stuff like that. What I want you to do is I want you to take just a couple minutes, pause this video if you need to, take a look at your notes, take a look at your book, internet, whatever works, and try to predict, based off the Arrhenius definition, what this is going to produce as a reactant. Or, excuse me, not as a reactant, but as a product. So just take a second. All right. So the answer is that's going to form a positive sodium ion and a negatively charged hydroxide ion. So since it produces negatively charged hydroxide ions, just what we just talked about, it means that it is a base. That's right. So it's a base. Let's take another look at another one. So in this example, which I'm going to do with a lot of examples in this video, is that I'm going to give you a compound, and I'm not going to give you the name. Particularly the reason why is that I want you guys to continue trying to memorize these compounds based off their formula and based off their structure. Because when it comes to tests and quizzes, I'm not going to give you both. I might just give you a name and no structure, no formula, or I might just give you a formula or a structure but with no name. So you need to really understand how to name these with nomenclature, or just kind of quickly identify them for your purposes later on in your assessments. So we have this substance and it's in water. So again, take a second, think about how this is going to react in regards to our Arrhenius definitions of acids and bases. All right. So it dissociates into hydrogen ion and this negatively charged chloride ion. Now, since it produced hydrogen ion, we know for a fact that it is a acid, correct. So this compound over here is actually considered or called hydrochloric acid, and this will be brought up in further examples down the road in this lecture as well. So just make a note of that, hydrochloric acid. If you need to use ChemDraw or Webster Dictionary or something to try to clarify the wording on that, you definitely can. You can definitely find it anywhere. So here's the more tricky one. So now we have this structure, and it's in water. So what I want you guys to really focus on, there are things there that you may not see. So use Lewis dot structures if you need to try to help you out and try to determine what the product of this substance in water will form in this reaction. So just take a second, take a couple minutes, do whatever you need to do. All right, so it's going to form this compound here. So this is called acetic acid. We use it a lot in lab. We will be using it a lot in lab, and you see it in every lab across the country and across the world. It's a very weak acid. It's actually vinegar. It's something you probably eat all the time, or maybe not, but vinegar is pretty much just diluted acetic acid. It's a weak acid, particularly, and the reason why is because it only lets go of one hydrogen ion. Now, you guys might be asking, well, where's the other hydrogens at? Well, I'll tell you what. So this carbon over here, that's actually not shown. Like I said, you probably need to draw it out a little bit. It actually has 3 hydrogens attached to it, but those hydrogens don't leave. So a strong acid is considered something that lets go of all its hydrogens at one time. And then a weak acid is something that's considered as it lets go of one hydrogen at a time. So something to keep in mind about, we'll talk about relative strengths of acids and bases as we move in more into the chapter and the unit. So just kind of start developing that in your mind a little bit. And again, this is an acid. So let's take it to the next level a little bit. Let's kind of take it into more critical thinking here. Let's try to apply what we know about Arrhenius acids and bases into a more comprehensive example. So using your knowledge of Arrhenius acids and bases, label the molecules in the following reactions with the appropriate labels that are associated with Arrhenius acids and base reactions. So we have an example. Again, I'm not going to label these. If you need to use ChemDraw or if you need to use the internet, try to figure out the names of these if they need to help you. Really try to just focus on the structure and what's really happening here. So what I want you to do is, one, if you haven't read the book yet, there is a section, I believe on page 665. It's right after the Bronson-Lowry acids and bases that we'll dive into later. It's in regards to conjugates. I recommend that you read that chapter because it does pertain to that, and it pertains to this question. Read that chapter. If you have questions and stuff, definitely bring that up. So yeah, just take a second to do that. All right, so there might have been a jump there for a little bit. Don't worry about that. So I hope you guys have already taken time to look at this problem. So first off, let's identify the acid. So the acid is this substance right here. It's actually considered phosphoric acid. Now, as you look on the other side, this phosphoric acid substance only lets go of one hydrogen ion. So it's considered a weak acid. So something to think about. Now, what is the base? This might be the tricky part of the question because it's not necessarily, on each side of the arrow. It's actually the water. So one little hint that you get is that this substance over here is actually water with an additional hydrogen attached to it. So that base accepts that hydrogen. So just kind of be aware of that. Again, we're starting to dive a little bit more into different definitions of acids and bases, but this is what that is. Now, thinking about these labels, hopefully you read that section. Now we're thinking about conjugates. So what is the conjugate base? Conjugate base is it's the substance after the proton but the hydrogen atom is emitted from that substance. So it's what's left over of the acid pretty much. In regards to the conjugate acid is the exact opposite of the base. So it's what becomes of the base after the hydrogen ion is attached to it. Something to just be aware of there. So now that we're talking about these conjugates and everything there, we're going to start diving into what's considered Bronson-Lowry acids and bases. So again, a little bit of background here. 1923, Danish chemist Johannes Bronsted and English chemist Thomas Lowry. It's very key here. Separately. They didn't even work together on this. They're in two different countries at the exact same time, and they just so happen to come with the exact same definitions for acids and bases. For this general definition of acids and bases. And this is the reason why it's called Bronson and Lowry, because these both submitted papers at the exact same time and with the exact same amount of credit. So just something to keep in mind. These guys did not work together. They just so happened to turn in the papers at the exact same time. So science is really odd world in that. So the definition they came up with, acid-base reactions involve the transfer of H+ ions from one substance to another. Now what you're asking yourself is like, how is this different from Arrhenius? Well, it comes really what they define as an H+ ion. So for aqueous solutions, a common factor molecule that can be seen in this definition of acid-base reactions is the following. So instead of considering just a hydrogen ion, they call it a proton. Now, as you remember from general chemistry, is that protons are a part of the atoms there. They're exact opposite in charge and pretty much the exact opposite in nice size. Protons are a lot bigger than electrons, but exact opposite in charge than electrons. But they just consider this with a hydrogen, because if you think about a hydrogen atom, it's a proton with an electron spinning around it. So if you take that electron away, that hydrogen becomes positive, and all you're left with is this proton here. So just kind of think about that in the atom model, as one can say. In regards to this, so what happens is you introduce a proton to water, and then it forms this complex that we've actually already seen before in the previous example called a hydronium ion, which is a water with an extra proton. And it gets this positive charge in the oxygen because now oxygen has these two lone pairs on it that you can't really see, but you probably see with Lewis dot structures. So these electrons attack this proton here, and they want to form a bond, but then it leaves a more partial positive charge on this hydronium ion. So something to just keep in mind there. So again, acids are defined by Bronson and Lowry as a substance that donates a proton to another substance. Bases is a substance that accepts a proton. Whoa. That was weird. Let's take a look at some examples here. So we again have hydrochloric acid and water. What I want you guys to do, same thing, pause the video, use whatever resources you need to, use this definition I just defined for you, and determine the products of this reaction. So just take a second. Alright. So the answer to this is that you get a hydronium ion with a chloride ion. Now remember, hydrochloric acid dissociates 100%. So it's already in water, so that water is going to want to grab this proton to form hydronium, so it leaves these chlorines floating about. It may even produce chlorine gas, depending on maybe how heated the solution is, or how what pressure it's at, so something to keep in mind there, but we're just going to think ionically right now. So we're going to take this, again, another example of the fact that I'm not going to tell you what the actual names of these compounds are, so again, use your resources, take some time, figure out the products to this reaction. Alright, so the answer using the Bronson-Lowry definition is it produces hydrofluoric acid and water. So this very far reactant on the left is the same thing as this hydronium compound up here. Instead of drawing the structure, I just drew the formula. It's definitely key to know both, because I could present both of them on a test, and I may need to get them in regards to reaction mechanisms or not. Or just a balanced equation, so it's something to keep in mind. So here we have a fluoride ion. Typically this is one of the Brinkelhoff diatomic gases, but in this case it's just an ion. Remember from your periodic trends is that fluorine is the most electronegative of any of the atoms on the periodic table that we know of so far anyway. So what happens is that proton from the hydronium complex must be promoted to the fluorine ion here, and it produces hydrofluoric acid. Now, ironically enough, hydrofluoric acid is considered a weak acid. Why is that? So, if you remember, fluorine is a very, very small atom. It has a very large charge density. So, which means is that when it draws that atom in close, because it's so highly electronegative, it wants to keep it so close to itself that it doesn't want to let go. It takes a lot of energy to let that hydrogen go. Therefore, it's a weak acid because it takes a lot of energy to pull that proton off. Now, hydrofluoric acid is probably one of the most dangerous acids you can ever deal with. More dangerous would probably be magic acid. Hydrofluoric acid, if you ever get it on yourself, if you leave it on your skin too long, it'll actually dissolve through your bones because it'll start binding to calcium. A lot of scientists keep calcium glutamate inside their labs. That way they can apply it real quickly to quench those fluoride ions before they do a lot of damage to a person. I personally do not like hydrofluoric acid because the labs I've been in that have used it are really scary, especially at Colorado State University. So definitely do not play with it at all. So you can't actually hold it in glass either. It'll actually dissolve glass. You have to typically hold it in like styrofoam. That's something that's like inert to everything. So there's something to be aware of. So now we're going to kind of dive into a little bit more interesting one. So again, we have hydrochloric acid, but now we have ammonia. So ammonia is something that you have in most household cleaning products. It's something that gives that smell there. It's a little bit more aromatic in that sense. So ammonia comes up with nitrogen with these three hydrogen atoms on it. It has this lone pair to it. So again, take some time, think about what you think the products of this reaction is going to be, and use the resources that you need to. Alright, so similar thing, going back to hydrochloric acid, it dissociates 100%, so you form these chlorine ions because they have nothing else to bind to. But then the proton from the hydrochloric acid goes and binds to ammonia to form ammonium. And so this is a positively charged ion, which you typically, it's a very hard thing to actually get sometimes, and is yet very useful. We use it a lot in the Haber process in regards to fertilizer. Something we'll probably dive more into examples with in class, as well as what's other things that we'll dive into as well. So let's level up a little bit. Let's go back into a critical thinking question. So let's kind of take this into more real-life applications, a little bit more further into chemistry. We're going to kind of go towards organic chemistry instead of gen chem. So in the field of organic chemistry, the use of aromatic compounds is very fundamental and essential to form particular reactions. And what they mean by aromatic is, one, they also smell, but it's in regards to electron configurations as well, which if you continue with your chemistry knowledge, you will find that aromatic compounds are very particular to certain numbers of double bonds and everything like that. So the most fundamental aromatic compound is benzene. Now, we probably have touched on benzene, maybe not, but it's a 6-carbon ring that has 3 double bonds to it, and it resonates throughout. So it's a very common thing. In organic chemistry, it's very useful. It's very versatile. There's like 20 different reactions you can do with just benzene alone, depending on what you have. So you can do a lot of things with benzene. One of the things you can do with benzene, as it says here, is one reaction is that you can go through nitration, which looks like this. So benzene is simply the 6-carbon ring. Now, the thing is that each carbon has 3 bonds to it, which only allows for 1 hydrogen to be attached to them on the ends. And then you put with these nitric acid and sulfuric acid, and it forms this nitrogen dioxide subgroup on here that replaces the hydrogen. Now, one thing that's really weird is that to make this reaction, there is 2 acids. So these 2 main catalytic acids undergo Bronsted-Lowry acid-base chemistry. So it's one weird way of looking at it is that acids don't always act as acids. Depending on what they're with, could define if it's going to be the acid, or an acid could be the base. Blow your mind a little bit, right? So we're going to kind of dive into this a little bit. So what I want you guys to do is that using that slide from before, that last slide, take that reaction, take the 2 main catalytic acids, add them together in their own separate reaction. I want you guys to define what you think is going to be the acid and what you think is going to be the base, and try to define or create a reaction mechanism to try to see how that nitrogen dioxide gets formed on the benzene. It's going to take some time. Use the internet. Use your resources and everything. Take some time to kind of come up with a good, solid reaction. I don't expect you guys to get on this on the first try, but just definitely something to think about. All right, so again, I don't expect you to get this on the first try. However, this is what you should be getting to. So what happens is sulfuric acid is the acid, nitric acid is the base. Sulfuric acid lets go of its proton. It gets put onto this nitric acid, onto this oxygen that has a negative charge to it. And then what happens is that there's this resonance of energy that goes through, and it kicks this water off into solution. And this water goes into solution, and it can actually help grab that hydrogen off the benzene there. And this hydrogen is what helps provide the cyclic reaction that happens. That hydrogen or that proton gets bonded right back to this sulfuric acid complex, or this conjugate base. And then it goes back onto here to actually form sulfuric acid again. That way it can start going more with nitric acid, which is really useful in organic chemistry because it helps increase yield of that nitration or nitration product of benzene. So in the end product, what happens is it forms nitrogen dioxide and water, in which this nitrogen dioxide goes and binds with benzene to form that nitration product that we want. So based off your knowledge in acid bases in regards to Bronsted-Lowry, I want you to appropriately label the components of this subreaction in accordance with the definition of what's presented in Bronsted-Lowry acids and bases. So conjugate acid, conjugate bases, acid bases. And then what I want you to do is that take a little bit step further. Take a few sentences to define why you think these labels are correct. So just something to think about. But definitely get those done and see how it works there for you. So we're going to go into Lewis acids and bases. I don't know why I didn't animate this slide, but whatever. So a little bit of background is it was produced by G.N. Lewis, same scientist behind Lewis dot structures that we've already dove into a little bit. And it was proposed. It didn't really specify the year in the book. I didn't really see anything, so I'm assuming it's in and around the same time as Lewis dot structures. So Lewis acid is a more general definition of acid. Instead of we're focusing on hydrogens or protons, we're focused on the exact opposite, which is electron pairs. So Lewis acid is electron pair acceptor, and the Lewis base is the electron pair donor. So it's kind of the opposite of what we've seen in the other two reactions, where the acid is kind of the perpetrator of the reaction. So in this case, the electron donor is the Lewis base, so that's what really ignites the reaction there. And this is a very useful definition for higher levels of chemistry as well as other sciences as well. So we're going to go back and take it back to ammonia. So ammonia, we take this complex and we put in this hydrogen ion, and what happens is that these electrons attack this hydrogen ion. So in regards to Lewis acids and bases, this is going to be the Lewis acid, and then hydrogen is going to be the Lewis base, which forms this neutral compound of ammonium. Well, not really neutral because it has a positive ion, but in regards to acids and bases, you can kind of think of it like that. Again, it can be a little bit confusing. I can answer questions in class and everything like that, but that's kind of what we're looking for. So let's look at some examples. So, all right, so we got these weird things here. All right, we got this ammonia ion. We also have this BF3 complex. So what I want you guys to do is use your book, use your resources, everything like that. And I want you guys to try to predict the product of this. I'll give you a little bit of a hint. There's only one product. So just kind of keep that in mind. All right, so it forms this weird complex. Now, we have to define what's the Lewis acid, what's the Lewis base. Well, what do you think the Lewis acid is? Let's think about it. What do you think gives its electrons to another? So, turns out this is the Lewis acid. Now, in regards to that, what it is, it's in regards to energies primarily. So, what happens is that this BF3 complex is at a higher energy than ammonia. This ammonia molecule is actually at a higher energy than this BF3 complex. And so in regards to energy, what we know about molecules is they want to get to the lowest stability energy that they possibly can. So that's why Lewis acid. So Lewis acid, I was wrong the first time, but Lewis acid is going to accept the electrons from the ammonia complex, which makes ammonia the Lewis base, which donates the electrons. So this ending product is actually lower in energy than pretty much this ammonia, but it's higher energy than this Lewis acid. So something to think about a little bit in regards to electron configuration and energy levels that we may have dove into in Gen Chem as well as earlier in the semester in AP Chemistry. So then we have water. In regards to water, we add carbon dioxide to it, which you guys should already know from a variety of classes. So I want you guys to think about what it's going to form in regards to the Lewis acid-base definition. Again, it's only going to form one product. So just kind of think about what you think is going to form. All right. So it forms carbonic acid, most commonly known as acid rain. So this is a reaction that happens in the atmosphere. Water binds to a lot of gets into this concentration of CO2, and it forms acidic rain. So it starts raining carbonic acid, which is kind of a weak acid. It's diprotic, so that means that it donates one hydrogen at a time and only has two hydrogens to get rid of. So it's something that happens in a lot of suburbs or cities like Los Angeles that has a lot of emissions and smoke and greenhouse gases. So if you ever notice on statues they have these weird like corrosions to it, it could be due to acidic rain. So what's the Lewis acid and what's the Lewis base? Well, let's kind of look at this a little bit. So in regards to this, the Lewis base is water. Because of those two lone pairs on oxygen, it wants to actually bind to the carbon a little bit. And then what happens is that the oxygens, it goes through this resonance process where this oxygen attacks this carbon and then attacks this oxygen. These electrons will resonate through this other oxygen, and then it actually grabs onto a hydrogen over here to form carbonic acid. We'll go through more mechanisms like that in class. It's a little complex for this right now. So yeah, again, that's a Lewis acid, is the carbon dioxide. So let's go on to the next. So critical thinking problem number 3. So I want you guys to complete this molecular orbital diagram, which we kind of done earlier in our AP chemistry classes in regards to electron configurations, energy levels, thermodynamics, and everything like that. I want you, one, to determine what elements A and B are based off their electron configuration. And then I want you to determine whether A or B or even both are either Lewis acids or bases and define why those qualities happen. So take this time to, see this. I don't know if this kind of covers it up, but there's another electron orbital right behind this camera here. Draw this in your scientific notebook. I'm not going to give you the answer to this. So I want you guys to write this, do the best you can, and then we'll answer this in class the next time I see you guys. We'll go over that together because it's a little bit more complex of a question, but I want you guys to start really thinking about how all this stuff comes into fruition in regards to acids and bases. So what did we learn today? We learned there's 3 types of definitions of acids and bases. The Arrhenius acids and bases, where acid releases hydrogen ions, bases release hydroxide ions. Bronsted-Lowry acids and bases, they produce acids are proton donors, and then bases are proton acceptors. And Lewis acids and bases, which acids are electron acceptors and bases are electron donors. So what I want you to do is I challenge you to do this to get more practice. I want you guys to go back to all the previous examples in this lecture and try to see if you can define different reactions with different definitions and different mechanisms. So if you go to the Arrhenius part of the lecture, I want you to kind of describe those examples with Bronsted-Lowry and Lewis acids and bases if you possibly can, and kind of vice versa throughout the lecture. It's not going to be graded or anything like that. I just kind of promote you to have a little bit more motivation and to kind of start thinking a little bit more critically like a scientist and just get a little bit more practice in. So credits and resources, like I said at the beginning of the lecture, these are the pages that you're going to want to read if you haven't already. So definitely take a look at those. Otherwise, I will see you next class or next lecture. If you have any questions, feel free to email me or feel free to come see me in class whenever you can, and I hope to see you soon. Take care. Have fun. Bye.